Hello, chat. Hello. So today we're going to be doing, and that is the wrong screen. But yeah, today we're going to be doing some chemistry revision. I haven't chosen what topic to do yet. I think paper one is on inorganic and physical chemistry, I believe. Let me check. Yeah, I think it's. Let me see. Why is physics and maths tutor taking so long to load on my phone? It's probably because my internet is just being not the greatest when I finally decide to go live. But yeah, so nothing has really happened. In like the past what? Not even the last day, but there's not a lot happened like today. But yeah, nothing really happened today. I was just like revising for chemistry because I've got it tomorrow. I've got chemistry paper 1 tomorrow. So I'll look for the let me see if I can look through the there we go, it's loaded. Okay, so I do believe it's like yeah, so it's like physical chemistry and inorganic chemistry, while paper 2 is like organic chemistry. I can't really bother explain what that means because I barely know what that means. Yeah, let me see. I kind of want to go over analytical techniques. Also, I'm fine with that. That's okay. Let's see. I think that might be. I am making sure like things does not fall off this chair right now. There we go. And not get blown off by my thing. Is it analytical techniques? Let's see if analysis was that. Is that what I'm thinking about? Yeah, I kind of do want to go over analytical techniques, but I'm fine with that personally. So, like, I don't really need to go over it per se. I don't think we'll go over that. Let's see. This is what happens when you keep way too much stuff on a chair. Okay, I'm gonna get one of my booklets out like we did for psychology. And you might I wanna see if I have one of like the first year booklets. Or like one of like the earlier stuff on it. Because I have been revising like a lot of like redocs and like some reactions and like year 2 content, but I haven't really been revising. Like I have been revising year 1 content. It's just quite a bit of year 1 is like organic synthesis and stuff like that. Like don't get me wrong, a lot of year 2 is also like organic synthesis, because it's also like you know, amino acids and amides and amines and stuff like that. Is this all just organic stuff? I think all that I think the rest of the stuff I've got is just organic stuff. Let's see. I have equilibrium, which I think I'm gonna talk through equilibrium because I really talk through that. And yeah, I can. It's fallen off. Okay, so yeah. So I have my fan on, and behind me it's been on pretty much all day since like 10 this morning ish. So let me get up this. I also got a new blank doc for chemistry revision. So equilibrium. So we're probably gonna get started, and I need to stop that slightly. We're gonna get started with a few definitions and stuff. So like, and just like then go into like a few like factors that affect equilibrium and just some other stuff. So so equilibrium is like when like the reaction is reversible, basically. So for example, with like water, you can like melt it by going from like ice to water, but then you can also freeze it again, going from water to ice. So that's like the most. That's not really a reaction. That's just I mean, I guess it is a reaction. That's like, but that's more of an enthalpy change. That's like enthalpy change. Not really enthalpy change of atomization. That's because atomization is changing something from its standard state into a gas. So and so and at some point a reaction will reach dynamic equilibrium, which is where the rates of the forward and backwards reaction become equal and the concentration of reactants and products do not change. And dynamic equilibrium only occurs in a closed system, which basically means that like nothing else is added to the reaction and nothing is like taken out of the reaction. So for example, in photosynthesis, like photosynthesis is like, if we take photosynthesis and respiration, if we just had those two reactions happening in a closed system, no more oxygen is added, no carbon dioxide is taken out. So rates of the forward and backwards reaction do not rates of forward and the concentration of reactants and products do not change. Okay, so we're going to go into Le Chatelier's principle. Chatelier. No, that's not how you spell it. Chatelier's principle. I need to get my switched out on my phone. I keep forgetting to do that. So this basically states if there's a change in either concentration, pressure, or temperature, then the equilibrium will like move to either the forward or backwards reaction to well, the equilibrium will move to one side of the reaction to counteract that change. So for example, when concentration changes, so this is like the most like, this is like harder to explain, and no, it's just like the most not convoluted, but it's just a lot to explain. So when the concentration of reactants increases, equilibrium will shift to the right. Again, will shift to the products to make more products. It's the same. Well, and if the concentration of products increases, equilibrium will shift to the left to make more reactants. Because, like we said, equilibrium is a reversible reaction. So for the forwards reaction, the reactants are the reactants and the products are the products. And for the backwards reaction, the reactants become the products and the products become the reactants. That doesn't make sense. That's a little bit convoluted, but you know what? We roll with it, honestly. We roll with it. Okay, and also the opposite will happen if the concentration of reactants will decrease and the concentration of products will decrease. So like whenever I say like, oh, concentration of reactants increase, so equilibrium will shift to the right. If the concentration of reactants decrease, the opposite will happen. Equilibrium will shift to the left. Okay, so change in pressure. So if pressure increases, this can be like if you like decrease the volume, or just like, I don't know, if you like decrease the volume, for example, so pressure will increase, and so equilibrium will shift to the side of the direction that has the least amount of like moles. So whenever you see like a simple reaction, you'll see like a number in front of the like compound. So for example, like 2H2SO4, that'll be like 2 like molecules of H2SO4. And if you're wondering, oh, what's the like 2 after H and like 4 after O, those are just like the number of like individual like reactants in the compound. Those numbers will stay the same. You just have to work. Okay, I'm not gonna go too much into it, but basically you'll have H2SO4. So this compound will have 4 oxygens and 2 hydrogens. If you put 2 in front of that, that's just times 2 of like every single thing. So that'll become 4 H's, 2 S, and 8 oxygens, 8 O's. So yeah, this will have the opposite effect if pressure decreases. Okay, changing temperature. So for a temperature increases, equilibrium will shift to the exothermic side. So for example, it will shift. If temperature increases, it will shift to the endothermic reaction to decrease temperature. And for this one, there we go. Okay, and a temperature decrease will have the opposite effect. So when temperature decreases, equilibrium will shift to, I keep forgetting to find shift. equilibrium will shift to the exothermic side. So for example, for a reversible reaction, for equilibrium, well, all equilibrium reactions are reversible. So if the forward reaction was exothermic and the backwards reaction was endothermic, wait, I can make a diagram, guys, to show you on direct and switch together. So if the forward reaction was let me just put X there. The forward reaction was exothermic and the backwards reaction, I absolutely love this feature, was endothermic. And then okay, yeah, it actually works. If the backwards reaction was endothermic, then then a temperature increase will cause equilibrium to shift to this side, which will cause a temperature decrease. And when temperature decreases, equilibrium will shift to this side of the reaction, will shift to the right side of the reaction. Of course, you have to check like enthalpy change signs and other stuff. Yeah, stuff like that. I absolutely loved mode. I completely forgot that this was a thing. Let me see. Is there anything really else on equilibrium? Ooh, there's the like the okay. So let me see. Okay, so the Haber process and has Nightshift just preemptively turned up on my computer? Because it looks like this side of my computer is just like slightly orange. Or maybe that's just, maybe it's just coming from a light, I don't know. So the Haber process is a reaction. So it's N2, so it's nitrogen gas plus 3 moles of hydrogen gas. And I don't have the reversible reaction signs on there, so we have to just deal. Which makes 2 moles of ammonium gas. And there's also an iron catalyst, and the enthalpy change of this reaction is minus 92 kilojoules per mole. You put like the -1 to show that it's like per mole. And the minus symbol of this enthalpy change shows that the forward reaction is exothermic and the backwards reaction is endothermic. The Haber process is carried under a high pressure of 200 atmospheres and a temperature of 400 degrees Celsius, which is 670 degrees Kelvin. That's like one of the only conversions I can easily remember, which is Celsius to Kelvin, because it's such like a specific number that I just easily remember it. And we did it a lot when we were doing like enthalpy changes, and using like the equations that require like temperature, such as the free energy equation, which is enthalpy change minus change in S. I'll just write it. I'll just write it on here. So the free energy equation is change in enthalpy minus temperature times change in S. I've completely forgotten what change in S. Well, I'm just gonna times change in S. That's the equation, and I love this picture so much. Yeah, this is the equation right here. So the reason why well, this isn't like the let's see. So the Haber process, like when like ammonia is being made and stuff, it may not always be carried out at like 200 atmospheres or like 400 degrees C. Mainly because of like cost. Like it's expensive to run it under like a high pressure and it's expensive to have it under a high pressure and high temperature. And yes, I know I said it goes to. Let me see. Yeah, so it's expensive to have it under a high pressure and a high temperature. So usually a lower pressure or like a lower temperature would be used, and a higher pressure and a higher temperature would be expensive. So I don't know if that makes sense, but you know. Okay, so do we actually have like a draw thing? Do we have a draw thing on here? So do we have a draw thing? So I can just like draw this in. Is that paint? Wait, what is this? I don't even know. Can I not have like a draw feature? Is there like not a draw feature like anywhere here? So I can like write out this like equation. Oh, I can just type it in here. So Kc equals, let me go the square brackets. C to the power of C. I don't remember what this second was. Oh, it's like asterisk, isn't it? D to the power of D. Let me just put that all in brackets so it's like on the same part of like the equation. Over. I'll explain what this means in a minute. Let me just actually write it in. Using Google Docs, I feel like a boomer. Yeah, that's the equation. That's known as the equilibrium. That's known as the equilibrium constant. And so this basically is, so let me just explain. So hello, welcome on in. Arthika, I think that's how you pronounce your name. Welcome on in, welcome on in. How are you doing today? How are you doing today? We're just going over a little bit of equilibrium today. Yeah, welcome on in, welcome on in. So this kind of takes from the general equation. So AA must be, and I will explain what this means in a minute, I promise. So this equation basically means products over reactants, and then each individual molecule is to the power of whatever number of moles, whatever number is in front of them in the reaction. So for example, if D was H2SO4, then lowercase d, and I need to reverse that. If lowercase d was 2, it would be the concentration of H2SO4 to the power of the power of 2. I think you can use moles for this, I think, but most of the time you'll have to calculate it using you have to calculate it using concentration. So essentially it is a worked example that I kind of want to go through. So calculate, I just didn't do my book, I don't know why. Calculate the value of Kc for the above reaction given that the equilibrium concentrations are, so there's HI equals 0.8 moles per decimeter minus 3. Concentration of H2 is 0.1 moles per decimeter. And concentration of I2 equals 0.2 mole per decimeter cubed. Determine the units of Kc, and I just received a comment on my video. I'm just gonna on my TikTok, so I'm gonna check it out real quick. Okay, I'm gonna get out my calculator just a sec. But you will have to determine the units. It's easy though. You literally just have to wait. I'll explain it in a minute. First, we need to work out the reaction. Did I write out the reaction? Oh no. I don't know if I did or not. Okay, I've got a few notes I didn't write the full equation. So, so it's H2 plus I2 equals 2HI. So the equation would be the concentration of HI, which is 0.8, over, where's it times or plus? I think it's times, yeah, I think it is times. Over 0.1 times 0.2, which equals 0.8, 0.1 times 0.2, which equals 40. Wait, what it would be if I added them together? 2.6. So I don't think it is like you times them together though. Otherwise it would say plus. But yeah, most time in equations when it's just like, oh, this next to this in square brackets, and they don't give any symbol, it's usually like you times them together. Yeah, so we will have to. Oh wait, I forgot the that this needs to be to the power of 2, so I actually got that answer wrong. So it would be 0.8 to the power of 2 over 0.1 times 0.2, and the answer would actually be 32, not 40. And to work out the units of this equation, so it would be mole per decimeter. So you'll just take the mole per decimeter to the -3, and I used the wrong thing here without even realising I used equals instead of minus. Mole per decimeter to the power of 2 over mole per dec -3 times mole per decimeter -3. Now, mole per decimeter squared is just basically mole per decimeter time. Hello Ace, how's the revision going? It's going okay so far. We're going over equilibrium, which is a topic I'm fairly like decent at. It's just I haven't gone over it a lot, so that's why we're doing it now. But yeah, it's going okay. So it's going decently so far. Ace, how has your day been today? How many exams do you have left? I have 5 total exams left. I have 2 biology exams left, and then all 3 chemistry exams. So I have another 2 weeks. I have another 2 weeks left of exams, which is okay. Yeah. Yeah, I have another 2 weeks left of exams, but after that, I am done. I need to revise for end of years, but it's a bit of a mess right now. When have you got them, Ace? When have you got them? I would recommend. I don't know if you do listen to me. It's in a week. Oh no. What I would recommend is if you do like listen to music, sometimes just like try and zone out and listen to like the same song on repeat. That's just kind of what I sometimes do. Like for example, I'll like listen to like Hell to Me, Heaven to You by Jesse Page on repeat. That has like a pretty good rhythm to it. Yeah, sometimes I'll listen to like a couple songs on repeat, or like one song on repeat for like an hour or two. And also like what I tend to do, I don't know if this will work for you. Sometimes I wish I didn't repeat, sometimes I don't mind. I don't know. Yeah, sometimes I like for me, I sometimes don't. Sometimes I'll just like listen to like all the songs on my playlist. Sometimes I'll just like keep one song on repeat. What I recommend you do is well, not what I recommend. What I tend to do is that I'll be like, okay, I'll start at 10:30, for example, and then I'll go for like 2 hours. Then I'll give myself like a 10-minute break of just watching TikTok, you know. And at that time, I'll just like try and zone out. I mean, yeah, so I'll be well, yeah. But yeah, I just try to block out like certain like parts of time, like, or like for example, like if I know I'm going out like somewhere, I'll try and just like get ready first and then do revision, you know. Sometimes it maybe just be best to like put some clothes on and then revise, and then just like after you've done your revision, just like get back in your pajamas or something, you know, or like, you know what I've been doing lately? When I, for like this past like week, after I've done like a long day revision or after I've done an exam, I'll literally go to the shop and buy myself chocolate peanuts or like a Fanta, you know, or like I'll go to Sainsbury's or something, you know, just like after you've done like a lot, just like try and do like, and try and mix up your revision if you can. I try and do that like maybe for one subject, just like copy out, like remake your notes, and for another just do like past papers or exam questions or something, you know, something like that. Anyways, for this question, so mole per decimeter to mole per decimeter squared just basically means mole per decimeter times mole per decimeter. So the top part of the equation is basically just the same as the bottom, so you can cancel, so you basically just cancel them out. So basically these are the exact same, so you just like cancel them out and just, yeah, this reaction would have no units basically. I think this might just be like some other like little bits, I guess. Oh yeah, so for this reaction you'll need equilibrium concentration. So let me make like a little table. So let me insert a table. What? Why isn't my insert working? There we go. There we go. Okay. I'm gonna move this onto the next one. So we're gonna write out like a little like example question. So 0.5 moles of Fe3 plus are added to 0.5 moles of Ag plus in a 1.5 decimeter cube solution. Upon reaching equilibrium, it is found that there are 0.3 moles of Se3 plus. And this is the equation. Ag plus aqueous into Fe3 plus, which I believe is also aqueous. Yeah. Plus Ag, which is a solid. So we don't actually need Ag as a solid. And this, like literally we only count like the aqueous like solutions. So we need Se3 plus. I accidentally just had my booklet like laid on answer. So Ag plus and Se2 plus. Now we need the like the ratios, which are just basically the numbers that will be in front of the reaction. So when there's no number inside in front of it, it just basically means there's like one of the compound basically. Then we need initial moles, which are these ones right here, so 0.5 and 0.5. Initial moles, the change in moles, equilibrium moles, and the equilibrium concentration. So the initial moles for Fe3 plus are 0.5. The initial moles for Ag plus are also 0.5. And the Fet plus at this point initially hasn't been made because it's a product, so there's no initial moles of that. Now the change in moles, so upon reaching equilibrium, it's found that there's 0.3 moles, so there's 0.3 equilibrium moles of Fe3 plus, which means a change of 0.2. And since reactants will be converted to reactants are converted into products, they will always have a decrease change in moles. And so this is where you'll need to use the ratios. So you'll need to times whatever the change in moles is by the ratio. So for example, if this was 2 instead of 1, because this is 1, you would times this by 2, because 1 times 2 is 2. But it's not all the ratios are. All the numbers in the ratio, okay, the stoichiometry. All of it is 1, so you need to just need to times 0.2 by 1, which is 0.2, which is the same. And same from here, except for the products, that is now going to be made. That is going to be now made, as you can see here. So that's going to have an increase in moles. So that's going to be 0.3, and that is going to be 0.2. Now, we literally need to now use the MCV concentration calculation, aka moles equals concentration times volume, to calculate this. So, and we have the volume here, which is 1.5. So just do a little bit of rearranging there. Concentration equals moles divided by the volume. So 0.3 divided by 1.5 equals 0.2. And this will be the same for this one here because it's the same. It's the same number. And then this one will be 0.2 divided by 1.5. This one is, these two are the same equilibrium, also have the same equilibrium concentration. So 0.2 divided by 1.5 is 0.1333 reoccurring. And then you would put those into your Kc equation. So Kc equals 0.13. I need to put square brackets instead of those curly brackets. The reoccurring 0.13 is over 0.2, and my voice is going dead, times 0.2. So it's basically 0.2 squared on the bottom. There. So 0.2 times 0.2, there we go. Which is 3.3 reoccurring. And just do the moles equation same you do for here, except it'll just be one moles per decimeter at the top, and then moles per decimeter and moles per decimeter on the bottom. So this will have the Kc units of just moles per decimeter to just moles per decimeter cubed. I think Is that it for? Oh no, we have gas equilibrium. Okay, I think I've been over this. And this is KP, by the way. I don't know if we'll get through a worked example for this one, but I'll definitely go over at least like the equation. So this is how. So as you can see, this is we used KC to work it out for aqueous solutions. Now we're gonna work it out for gases, and I need to sort out my. There we go. Okay, I'm gonna need to work it out for gases, which is where the KP which is where the KP equation comes in, and then you actually need 3 separate equations just with KP, but we'll get onto that in a minute. So we need the partial pressure of the products I'm gonna write this in as an equation. Insert what kind of insert equation? Insert, I believe. Equation. Not there. Here. Insert equation. So KP equals the partial pressure of C to the power of C times the partial pressure of D. So we need the partial pressure of the products on the top, and then the partial pressure of the reactants on the bottom. And so what you need the equation to work out partial pressure is so the partial pressure of like one specific like thing, like one specific like reactant or product or compound in the equation is the mole fraction times the total pressure. Now you will be given the total pressure in the question, but you might not be given the mole fraction. So to like work the mole fraction out, you need the number of moles of a specific compound over the total number of moles in the equation, or like in the entire like in the entire question. So actually I'm gonna do like talking through one worked example. So let's see. So the equation is 2SO2 as a gas plus O2 as a gas equals 2SO3 as a gas. So, and in the question it states that we're given 3 moles of SO2, 4 moles of O2. So those are the initial moles, and we are given the equilibrium moles. You know, let's just actually put it into the table. So 1, 2, 3, 4, 5, 6, 7. Okay. There we go. That should do it. So we need SO2, O2, and SO3. And then we need the ratio, the initial moles, the change in moles, the equilibrium moles, the mole fraction, and the partial pressure. And also we'll do our little KP equation. So our little ratios, the stoichiometry. I just don't know how to say that word. Stoichiometry. I don't know how to say that word. So 2, 1, and 2 for each respectively, because they're these numbers in front of the compound. So we are actually different. Got some initial moles. So 3 initial moles of sulfur dioxide. 4 initial moles of oxygen, and 0 initial moles of sulfur trioxide. Now we are given the equilibrium moles of oxygen, which is 3, which means that this had a -1 of change. Now since this has a ratio of 2, that means the change in moles is -2, and that means the equilibrium moles of SO2 is 1, and that means that this has a +2 change in moles, and so the equilibrium moles are 2. So the equation for how you would calculate the mole fraction for each of these compounds. So for SO2, you'll need to do 1/6, because that's the total number of moles, which is 0.666 reoccurring. 3/6, which is 0.5, I believe. I always have to check this. Yeah, 0.5, and then 2/6, which is 0.323 reoccurring. Now to get the partial pressure, we are given the partial pressure of 50. So what we need to do is do 0.666 reoccurring times 50 times 50, which is 8.333 reoccurring, and then 0.5 times 50, which is 25, and then 0.333 times 50, which is 16.666 reoccurring. And so we need to put that into our KP equation. So that'll be 16.666 squared over 8.323 squared times 25. So let me work that out. So that is I literally have to keep like the reoccurring and to get the most accurate thing, I have to like put in like 2/6 times 50, you know. So this may take a little bit. Six. So 2 should be squared, and then times 25, and that's equal 4. Oh wait, I didn't do 1/6 times 50. Yeah, and so for that, I got 0.16 kilopascals. To the -1, you will have to work out the units for this one, and this one is just kilopascals to the -1, and I think that's basically it for like equilibrium, basically. Yeah. Also, I am thinking of I'm just gonna like start putting my stuff away. So what I am thinking of doing is like when I have like finished all of my exams, is to put like all the revision stuff we've done over like the past few weeks on like Twitter and stuff. So like if you are like doing your A levels or like thinking of doing like psychology and chemistry A levels, we probably won't be able to do biology revision because in like the next 2 weeks, all my chemistry, like in the next 2 weeks I have I think this is public information, but you know, I have chemistry paper 1 on. I have chemistry paper 1 before biology paper 2, so I obviously won't be streaming during the week, so I won't be able to do biology revision then. And then I have and then the week after that I have chemistry paper 2 the week after that. And did I get? Oh, it's just someone's having Snapchat boot. And let's see if there's anyone I want to raid. No, there's no one I really want to raid. I'll probably do like a little bit more revision for chemistry. Like tomorrow morning. Yeah, I hope you have enjoyed the stream. I'll like highlight this